Hello everyone, can you hear me? Okay, great. So I think we lost a minute there. Don't know what went wrong. Okay, so multiplying that all out, the tangent line will be y equals x. So now I draw my graph. Yes. Oh, thank you. Okay. So my graph of 1 over x looks like this. And my point, minus 1, is here. And my tangent line, according to my calculation, is this. I'm just going to dot it. Okay. Okay, but this is cutting the curve. So unfortunately, y equals x must be wrong because it cuts the curve. So let's go back and check where our mistake was, and we spot this mistake here. So maybe I'll use green so we can see. So sound is alive, good. Green's not so easy to see either. Let's use orange. So we have a -1 there, gives us a -1 here, and a -1 there. And we get -1, what do we get? And so minus x minus 2. And then if we sketch that, we get, I'm hoping, this tangent line here. So the tangent line you can see from the graph, and we check the x and y intercepts. Yes. So y-intercept is -2. And x-intercept is also -2. Okay. So the point is you can use your graphs to check your calculations. And you can use your calculations to check your graphs. So another point about graphs, so about detail. So you'll have noticed in class my graphs aren't that accurate in numerical terms. I mean, I could do something like this. I could plot the so what do I want? So 3 here, 6, so on. Okay, so I'm enjoying doing this because this is the kind of thing I don't usually have time to do in my job. Okay, and then I can join the points. Something like this. Okay, that wasn't very straight. Okay, so something like that. And I want to say that this is great. But it's also, but it is more detail than is needed. If question says draw, or sometimes questions say sketch the graph. So just on a point of language, if it said plot, then maybe it would be asking you to do something like this. But if it says draw or sketch, then just something like this, which I've done many times. This is good enough. So I guess what I'm saying, the graphs you draw in exams don't have to be better than the ones I draw in lectures. So good enough. Okay, so yeah, although there's the thing about the important features. So I've got to be careful, for instance, that went vertical here. So check that it's not going vertical, for instance. I'll show you another important thing. Okay, but about the details we do have to show. But note, for instance, with y equals 1 over x minus 1. So, well, let's do y equals 1 over x plus 1. That's slightly more convenient. So this, well, 1 over x has an asymptote, the x-axis. So 1 over x plus 1 has an asymptote, this line x equals 1. So 1 over x plus 1. Okay. And the x-intercept is minus 1. So that's good enough. But if I did, let me try and do it. If I did something like this, yeah. So something like that. Okay, so even if I still have that x-intercept right, you see I've not shown this line x equals 1. So, because this tail on the left is higher than the tail on the right. So, yeah. So unfortunately, this one is not good enough. No. Okay, so let's see if had any further points on that. Yeah, just one particular graph, which was more difficult than the rest. So let me say a word about how to get that. If I want to sketch y equals 1 over 1 plus x squared. So this is a good example. Chain rule gives me a 2x from differentiating the 1 plus x, and differentiating the 1 over something squared. Sorry, from differentiating the 1 over something, I get minus 1 over something squared. Okay, let's sketch. And the tangent was 1. So using that, we get that the tangent line is y equals x. Okay, so we can sketch that. So what have we got? Yes. So that tangent line has intercepts 2 and 1. And the point where it touches the curve is this. So how do we sketch it? Well, I think the best way to think about it is to combine 2 points. Let's call them A, that at x equals 0, y equals 1, and y prime, well, we can see equals 0. And B, for x large, um, 1 over 1 plus x squared is approximately 1 over x squared. So the 1 plus doesn't make much difference. So, putting this together, the graph has a horizontal tangent at x equals 0. So let's mark that bit of information A. And for x large, it looks like 1 over x squared. And we already knew how to graph that. I've tried to graph it there. You put together these 2 bits of information. So putting together A and B, and that, that the line is tangent to curve, we get so I'm going to draw it into this one. Maybe in blue. So horizontal tangent here, tangent to the curve, and then the curve goes like 1 over x squared. So like that. So I've only drawn half of the curve, and you get the other half by evenness. So that's Okay, so one final point on graphs. Note. So maybe your iPad has feature like this. So I can draw a circle, maybe not. Yes. So please do not use for homework or exam. As some people do not have. Okay. I'm trying to draw an example of a circle that's good enough. Yeah, okay, so this is some good enough. But I think we did not mark that down because I didn't mention that issue before the exam. Okay, so let me know if there's any questions there. And if not, we can... No, so my point is it's good to draw the circle as well as possible, but with your own hand. I mean... Okay, so let's continue. To calculate some definite integrals. We're going to get a lot better at calculating definite integrals very soon. So let me just recall what we calculated last time. So of x we had this. So note so we proved for a less than 0 less than b, but it holds by similar methods for all a less than b. Okay, let me add another thing we proved. The integral of a constant, or let's just take 1 to be simple. The integral of just 1 is the difference between the limits of integration. And that matches with the area under the graph interpretation. Both of these things can be thought of as areas under the graph of a constant function 1 or the function x. Okay. So note also we can prove, let's not go into the details, but by the same methods, if I take the integral of x cubed, then there's a pattern. I get b cubed over 3 minus a cubed over 3. Okay, so this is a pattern that we'll extend today, and we'll be able to calculate many more definite integrals. So let's size using these facts. So recall also, so yeah, thank you, point out a mistake here. I meant x squared. Yeah, so, okay, so now let's look again. The pattern is clear. The power goes up on the x, and the powers go up on the right-hand side as well. Okay, and we recall for f integrable on AB, the average value that's, I'm going to write it av f, is this definite integral divided by the length of our interval. So let's do an example to remind us of our rules. So let's calculate the average of cx plus d, that function, on the interval a to b. So this average, well, using the formula, it's 1 over b minus a of the integral of cx plus d dx. And we proved some rules last time for how definite integrals work. So one of them was that integrals are additive. So if I'm integrating a sum, then that's a sum of integrals like this. So that's the additive rule. And then C and D are constants. So if I'm integrating something times a constant, it gives me a constant times the integral of that something. So we get this. So that's the constant multiple rule. And then above, we wrote down the values of those two integrals I have there. So isn't deta, good point, good point. So that's not a mistake, but it's a good point to look at because it can be confusing. So this note This is just part of the integral sign, integral notation. And it's not d times x. Okay, I hope that's clear. So the two d's, even though they're next to each other, mean different things. So the first d is a constant. Let me say that, if it wasn't clear. So these c and d's are constants. But the other d, the d I've put in a blue circle, is part of the integral notation. Yeah, so it can be confusing, unfortunately, but this is the way these things are written. Okay, so using the results above, I get this, and I can simplify that. What do I get? I get half c b plus a plus d. Okay, so now let's just check that answer. So check. This is average of CA plus D and CB plus D. So I'm going to draw a graph to show why that makes sense. So say our interval is between A and B, and our graph is CX plus D. I made that a bit too high. Our graph is CX plus D. Then the values at A and the values at B have the average halfway between them. Okay. Okay, so let's take a break. Okay, so back to rules. From last time. So the first is a definition that usually we integrate with a less than b. This right here, but if we change around the if we change around the order like this, then we put in a minus sign. Yeah. If I integrate between a and a, I'm 0. Constant multiple in sum, we just said. And this rule about additivity, so integrating from a to b and then b to c, I can do in one go. Okay, and we had pictures which explained why those happened. And so then we just have this 6 and 7. So call it the max-min inequality. And this is quite important theoretically. So let's say something about it. So if f has maximum m, big M, and minimum little m on a to b, so I'm writing it a bit shorter than before, then that minimum tells me a lowest possible value for the integral. And that lowest possible value is the minimum times the length of my interval. And I also have the highest possible value given by the maximum. Okay, and this makes sense because I think I have the graph. So this one, so we're comparing areas. The area under the blue graph is greater than or equal to the green box and less than or equal to the big box. So that's what this inequality is saying. But let's prove it. So proof. So recall this Riemann sum. The sum of the values at some points, ck, times the width of certain integral interval. Good, I'm summing over n intervals. So this was just calculating the areas of some boxes that approximated the area under the graph. And now I can compare this with m equals b minus a. So b minus a is the length of the whole interval. So that is the sum of the lengths of the subintervals. And I can take that m inside. And because, by definition of the minimum is less than or equal to all the values, I get this inequality for the sums. And in the other direction, I get an inequality for these maximums. And I get this. So that's the proof. That. And then we have a domination. So let me just write it down. If fx is greater than or equal to gx, then the same inequality holds for their definite integrals. And we can see this from the picture. So the area under f is greater than or equal to the area under g. And so that's saying this. And so note can also prove this with Riemann sums. Prove using these Riemann sums. Okay, so that covers the facts about integrals that we'll be using. And now, starting a new section, some powerful methods to calculate them. So, the mean value theorem for integrals. So recall that for f on AB, new page, the average of f is the integral divided by the length of the interval. And the mean value theorem says that, in fact, at least for f continuous, this value is always taken by the function so what do I mean? Or theorem. For f continuous on AB, then at some point C in that interval, we have that FC equals this average value. So we can actually prove this by the, did we call it the min-max or the max-min inequality? I'm not sure. By the max-min inequality. So remember, this was saying that the integral from a to b of fx dx was larger than something and smaller than something else. And those somethings both had a factor b minus a. So we can divide through by that factor. And get this. So that's actually saying something quite obvious, intuitively, that the average value is between the minimum and the maximum. But then recall that by the intermediate value theorem, for any such star, we have some C such that FC equals star. Okay, and that is what the theorem required. So remember, the intermediate value theorem was a property of a continuous function. Okay, so let's do some examples of this. So for example, fx is 4 minus x on 0 to 3. So we have our formula for the average of f, gives us 1 over 3, integral 0 to 3, 4 minus x. So this is good practice. So it's 1 over 3 times 4, integral 0 to 3 times 1, minus integral 0 to 3, of x dx. And so I get 1 over 3 times 4 times 3, the difference between the limits, minus 3 squared over 2. So using what we had before. So what do we get? We have to do some mental arithmetic. So this is 12. It's also 24 over 2. And this is 9 over 2. So I get 1 over 3 times what? Times 15 over 2. Oh, great. This is looking like 5 over 2, which is what I hoped. Okay, so we can draw a graph. So y-intercept is 4, and our interval is 0 to 3. And the value at 3 is going to be 1. So we have this point here. So this is my graph. I'm not drawing very straight yet. So the average, this is saying, is 5 over 2. So it's 5 over 2, that's 2.5. Ah, okay, so yeah. So it's what we said before. It's halfway between the two endpoints. So this 5 over 2, halfway between the value at the two endpoints. And that the value occurs at 3 over 2. Just looking at the formula for the function. So in this case, we can put c equals 3 over 2 in that theorem. So if I put c equals 3 over 2, then the value fc is equal to the average of f. Okay, so that's a simple example, but so no, as before with the intermediate value theorem, we cannot always calculate c explicitly. So for example, say f is continuous on AB, and the integral from A to B of fx dx is equal to 0. Well then, fc equals 0 for some c in AB. So i.e., f has a root in this interval. And this follows immediately from the theorem above. So to draw a picture, you remember that if a function has some positive values and some negative values, then when I do an integral, say from a to b like this, and then these can cancel out. So something like this is an example of this situation. Okay. So now, very important, using what we've established there, we can start to use and prove what's called the fundamental theorem of calculus. Okay, so we start with f, a function of t, and say it's integrable on some interval ab. And then I can use definite integration to make a new function. Let's call it f of x. And what I'm going to do here is a definite integral of ft, but where the limit, the upper limit depends on x. So it won't be obvious why we're doing this yet, but it will become obvious soon. So this defines a function with the same domain. AB. So let's just note that, for instance, f of a at the left-hand side of the domain, in that case, the limits of integration are the same, and so we just get 0. But you can imagine if ft is positive, then as I increase x, then I'm measuring the area under that graph. So let's get a picture for this. Okay, and the reason why we're writing down this function big F is because we want to ask what is derivative of fx. Okay, so let's emphasize this key question. So remembering our definition, f prime x So the derivative function evaluated to x, we get this by taking a limit as h goes to 0 of this quotient, which is the slope of the graph of big F. Now, I've not drawn the function big F here, I've drawn the function little f. But we can evaluate this limit. So let's start by doing that roughly, and then I'll do the proof. So the numerator, well, I'll do the proof a bit later, is this difference. And so what is fx? Big Fx, that's the area above in blue. But what about Fx plus h? So that's the area in blue plus something. And the thing that's being added is shown in this new diagram in purple. Well, to be more precise, what I'm adding is a bit more area under the curve of the graph, but that purple box is approximately that area. So the difference is approximately the purple area below. And that is a box of fx and width h. So it seems that the limit is h goes to 0. Well, let me write it a bit differently. Well, this limit star should be equal to f of x itself, because the top is f of x times h, and then we're dividing by h. So if our calculation is approximately right, we should get f of x. In other words, f prime x, so the derivative of this function big F that we made should be the original function little f. So in fact, we can prove theorem. So this is fundamental theorem of calculus part 1. So it's divided into 2 parts in the book, and for good reason. So let me say part 1, and then we'll give some examples and prove and explain part 2, and then we'll come back and prove part 1 later. Okay, so if f is continuous on AB, then if I make big F in this way by integrating from A to X, this is also continuous on A to B, and it's differentiable I have to be a bit careful here. It's differentiable on the open interval AB with f prime x. So I can write that also as d by dx of this integral so that derivative is fx itself. Okay, so let's give a few examples of that. Maybe I'll give it a bit of space. So for example, just substituting in a particular function here, d by dx of the integral from a to x cos t dt, that just gives me back cos x. So there I'm taking the function to be the function cos. So notice, as in the theorem, we have ft and fx, and so in the same way we have cos t and cos x. So it's the same function, but with different variable names. Okay, and I can also fix, instead of taking an endpoint A, I can take a fixed endpoint 0. So say 1 over 1 plus t squared dt. So that would give me 1 over 1 plus x squared. Okay, so I think I will give a proof of that and then go on to the second part. So proof. So we have this definition of f of x, and we want to work out the derivative of this big f of x. So remember that the derivative was a limit, and the top part of that thing that you were taking the limit of was this. So by definition of big F, this is this difference of integrals. Okay. And now, this first bit, well, remember we had this additivity rule for integrals, that if you integrate from a to x, and then from x to x plus h, then that's the same as integrating all the way. So, okay, let me write this a bit differently. So this sum gives that integral. And so there's a cancellation here. So this equals the integral from x to x plus h. So again, when we calculate the derivative of big F, we have to take this top bit and divide through by h. So by what I just said, that is equal to 1 over h times this integral. And that is equal to the average of f on the integral x to x plus h. And we showed that there is always some c such that f of c equals the average. So some c in this interval. And so, when we calculate f prime x, that is equal to the limit of this fraction here but that is equal to f of c for some c in between x and x plus h, and as h goes to 0, the limit must be fx. Okay. So that is the proof of this part of the fundamental theorem. I'm going to rearrange this because I think it's not that clear. Okay. I hope that's better. Okay. Okay, so that was fundamental theorem part 1. Where we took our function little f and made a big F and showed that its derivative gave us back the original function little f. But now part 2 says this, that if little f is continuous on a and b, on the interval a to b, and now big F takes a different role. Big F is any antiderivative of F on AB, then the definite integral from a to b of fx is very easy to calculate. It's just the difference of the values of big F at the endpoints of the interval. So this is extremely powerful because it says whenever we can find an antiderivative, we can calculate definite integrals. So far we've been struggling to calculate definite integrals one by one using sums and things like this, but this shows that we can calculate very much more easily than that, and that's what we'll be doing for the rest of the course. Okay, so just see if there's any questions. No, so I'll give a proof of this and then we'll take a break and then I'll show examples. So proof, assuming part one, which was the hard bit actually. Have that, I'm going to change letters. I have that gx, so this is defined in just the same way as our old fx, it just uses a different letter. So we integrate from a to x, ft dt. And what part one was saying is that this function, whatever we call it, this gx is an antiderivative of f. Now, remember that if g is an antiderivative, then any antiderivative is of form fx is gx plus c, where c is a constant. Okay, so we discussed this last time. So we can assume that the big F in part two of the theorem is of this form, gx plus c. But then let's evaluate the right-hand side, fb minus fa. So by this formula, can write it in terms of the g's, and those c's of course cancel. So gb minus ga. And then let's look at this definition. Okay, we'll finish this after the break. Okay, so the trick is noticing that this is 0 because the limits of integration are the same. And so this is the integral that the theorem was talking about. So running this equation backwards, we say that that definite integral is fb minus fa the difference of two values of the antiderivative. So notation, we write the antiderivative with just a bar for this difference. So you'll see that makes the calculations nicer to write. So also in the book, you'll see this square bracket, this, or square brackets on both sides, like that. So all these notations you'll see. So let's do some examples. So for example, if I integrate sine x from 0 to pi, let's remember the graph. So something like this. Maximum value 1, pi over 2, and we have that if I put fx equals sine x, then big Fx minus cos x is an antiderivative so by theorem part 2, we have that the integral from 0 to pi of sine x is minus cos x at pi minus cos x at 0. Okay. And, well, let's remember how the graph of that looks so we can see what these values should be. So cos x starts at 1 goes down to -1. So 1 goes down to -1, like that. And so putting in these values, I get -1, which is +1. And then again, -1, which is +1. So we have an answer 2. And so reusing this graph at the top, and because sine x is non-negative on this interval 0 to pi, this gives area under the graph. So let's write that in. Here, I'm going to do that better. So here, we have that this area is 2. And so, remark, so this is just an amazing result. So how else could you possibly calculate and it really shows the power of these derivatives and antiderivatives and integrals that we've been studying. Okay, so a few more examples. Yeah, I mean, of course, the power of this technique is not just one calculation, that we can calculate the areas under a whole range of graphs, and that we'll be able to apply this to calculating physical quantities, all sorts of things. And a lot of the end of the course is about that. So let's a bit more quickly do another example with cos x. So cos x, we have that sine x is an antiderivative. So the theorem tells us that I can calculate this definite integral by taking a difference in values of that antiderivative. Okay, I'm going to move this around a bit to make it clearer. So I'm writing this in the shortened form now. This is the way people usually write it when they're calculating. So sine x with this vertical line on the right and the limit 0 and pi. And then that is by definition sine pi minus sine 0. And from the graph above, that's 0 minus 0. So what are we seeing here? Well, again, let's reuse this graph label. So this is sine x, and this is cos x. So in this case, sorry for this bouncing around. In this case, we get 0 because positive and negative values cancel. And so we saw something like that before. We'll say a bit more about that later on. So yeah. So one more example. Those were with trigonometric functions. But we can also work with powers. So if I have 3 over 2 root x minus 4 over x squared dx, how to calculate that? Well, I find an antiderivative. So in this case, x to the power 3 over 2 plus 4 over x, that's an antiderivative. And I take a difference of its values like that. So what do I get? 4 to the power 3 over 2 plus 4 over 4 minus 1 to the power 3 over 2 plus 4 over 1. So what's that? It's 8. Square root of 4 is 2 to the power 3 is 8 plus 1 minus 1 plus 5. And so that's 4. Okay. So we can now take these really complicated integrals and get simple answers out. So a first application of this is to calculate areas, and there are many more applications to come. So areas using antiderivatives. So for example, calculate the area bounded by the graph of y equals 6 minus x squared and the x-axis. Okay, so questions are often phrased like this, and to understand what that means, we have to sketch a graph first. So the axis of this parabola is x equals minus a half. Oh, x equals minus a half. So recall the formula is x equals minus b over 2a. And we can factor it as y equals 3 plus x times 2 minus x. So to sketch this, let's calculate the value on the axis as we did before. It's y equals, well, I'll use the, what will I do? Yeah, maybe I'll use the original equation. So it's 6 6 plus a half minus a quarter. Sorry, something a bit wrong with what I calculated before. Just a moment. 6 plus. Yes, okay. So 6 plus a half minus a half squared, which is a quarter, like we said. So that's 6 1/4. And 6 1/4 is 25 over 4. Okay. Great. Okay, so that's enough information to make a graph of the function. And let's do that down here. Or take the graph from the book like this. So we're asked for the area bounded by the curve and x-axis. So the required area is blue region. So the area equals so here I'm going to take the calculation from the book because the calculations are the same we've done before, but takes a bit of time to write out. So we integrate from -3 to 2 our function. So there's an antiderivative of our function. It's 6x minus x cubed over 2 minus x cubed over 3. And we evaluate that with limits -3 and 2. So if I put in 2, I get 12 minus 2 squared over 2, which is 2, minus 8 over 3. And if I put in -3, I get something more complicated, but finishing up the calculation, I get 20 5/6. Okay, and so, yeah. So that's the area under this blue parabola. So notice, last thing to notice from this example is that this area is equal to 2/3 base times height. So why? Well, this equals 2/3. The base is 5, and the height is 25/4. So I just want to check that this comes out as the same thing. So we have 2's cancelling. To give this 2. Yeah, and then I have, so 125/6, and that I hope is going to, yes it is, it's going to be 20 5/6. So this is like the formula area equals half base times height for a triangle. Okay, but now we can make these formulas for all sorts of different curved shapes. Okay, so another example. So let's calculate the area between a graph of sine x on 0 to 2 pi and the x axis. So this is a graph of sine x. Going between 1 and -1. And we know that it's 0 at pi. So less than pi, it's positive, and more than pi, it's negative. So we want to add up this blue area. And this red area. So the blue area we already calculated. That's the integral from 0 to pi of sine x dx, and that was equal to 2. And what about the red area? Well, let's calculate the integral from pi to 2 pi for some more practice of sine x dx. So we find an antiderivative, minus cos x will do, and we go from pi to 2 pi. And now, cos x at 2 pi is plus 1, so we have a minus 1, and then we minus cos x at pi. So that's minus minus 1, which is plus 1. And so the answer is minus 2. And that equals, well, it's clear in this case that it equals minus the red area. So the integrals between the points where the function is 0 give us areas between the graph and the x-axis, but maybe with a sign. So the required area is 2 plus the absolute value of minus 2. So let me just write, this one is the integral from 0 to pi, and this one is the integral from pi to 2 pi. So let's summarize and do another example. So to calculate the area between the graph and the x-axis. So we first we subdivide AB into subintervals according to the roots of f, so the places where f is 0. If they exist, they may not. And 2, we integrate on each subinterval. And then 3, we sum the absolute values. So let's give an example to explain. Let's take fx is x cubed minus x squared minus 2x on the interval minus 1 to 2. So this is going to factor. We have a factor x, and then x squared minus x minus 2. And then I can factor more, I think. Yes, x minus 2, x plus 1. So the graph has roots at minus 1 and 0 and 2. So did I get a graph of this function? Maybe not. Okay. But let's see what we can say. So f prime x is 3x squared minus 2x minus 2 so that's maybe not so helpful. Okay, so maybe it's best if I just do a rough sketch now and add a graph later. So the roots are, we said, minus 1 and 0 and 2. So let's do a rough sketch. Get this for fx. So we have two regions. Let's mark them blue and red. So we start with interval minus 1 to 0. So the integral of fx on this interval is given by writing down an antiderivative so we can do x to the 4 over 4. So if I differentiate that, the 4's cancel and I get an x to the 3. For x squared, I can take x3 to the 3 because the 3's cancel and I get an x2. And for 2x, I can take an x squared. And then the limits, minus 1 and 0. Yeah. So evaluating, we get, well, for the top limit, lots of zeros. And then for the bottom limit, 1 over 4 minus minus 1 over 3, so that becomes a plus, and minus 1. And so what does that give us? 1 minus a quarter minus a third. And so that is 12 minus 3 minus 4. Giving 5 over 12. Okay, so a bit less than 1 from the blue region. So it's quite amazing that I didn't even have to be able to draw the graph properly to be able to say what the areas are. So let's do this other one. So 0 to 2 fx dx. Okay, so up here I've made an easy mistake to make, but a mistake which you should not make, and that's to always put that dx to say which variable you're using in the integral. Okay, so the same antiderivative is going to do the job here as well. I change the limits now. And get this. And now I calculate. So 2 to the 4 over 4 is 4. Minus 8 over 3 minus 4. So those are going to cancel. And then, again, we get a bunch of zeros. So that one is just minus 8 over 3. And so now the area between, so the required area is my 5 over 12 from the blue bit, and from the red bit, the absolute value of the integral, minus 8 over 3. So you can see that's giving the red area between the x-axis and the graph. Okay, and so let's finish the calculation. We get 5 over 12 plus 8 over 3, and that gives 5 plus 4 times 8 over 12, and that is 37 over 12. Magic. Okay. So we're nearly done for the day, but let me, well, actually, let me not start the next topic. So the next topic is about how to calculate indefinite integrals. So let me just leave that till next time. Calculating indefinite integrals. And we'll continue that on Thursday. Okay, thank you. Class is finished.